Hi, I'm Jim Phillips, and I've been receiving a lot of questions about the next edition of IEEE 1584. We've been working on this standard for, well, actually it's been 16 years since the original 2002 standard came out. So what I would like to do is give you a little bit of a rundown on what's happened in those 16 years, as well as talk about, well, what some of the major changes are going to be in the next edition. But before I begin, like I do with most talks that I give, I'm required to give a disclaimer, and that is that what I'm about to say doesn't necessarily reflect any view of the standards such as IEEE or NFPA, ANSI, or IEC. And why this is particularly important is because I'm the vice chair of IEEE 1584, and I'm also on the steering committee of the IEEE NFPA Collaborative Research, and I'm also the international chair of the IEC Live Working Standards, so I'm kind of pretty deep into all this. So I have to make that disclaimer that this whole video is going to be my views, and you know, as I said, may or may not necessarily reflect the views of some of these other standards. So with that, 16 years, and the last several years, it's like back in the days of family vacation, when I would keep hearing from the back seat from my kids when they were younger, are we there yet? And a little bit later, are we there yet? And are we there yet? Till I'm about ready to lose my mind. We've been at this for a while. And I think the last 16 years can best be summed up by one of the rock legends from the 60s and 70s. And I think it could just be stated as, what a long, strange trip it's been. The infamous Jerry Garcia from the Grateful Dead. So I want to give you a little bit of a history of what has gotten us to this point. And this point right now is actually early August 2018. So if you see this sometime down the road, keep that time frame in mind. IEEE 1584 was published in September 2002. And when it came out, it was widely celebrated because it was the first standard of its kind that gave you methods to actually calculate the arcing short circuit current, the incident energy, and the arc flash boundary. And so it was considered a landmark standard at the time, except it didn't take too long after this came out, and there were challenges. And the challenges came from a few, mostly from a few international experts, and they looked at it as, okay, well, this is what you've done now, but what about? And they began to look at what about X and Y and Z. And so after we heard enough of that, started thinking, okay, we need to move this to the next level. But the next level was going to be a pretty formidable task. So a collaboration effort was put together between IEEE 1584, and NFPA. And so this collaboration, known as the IEEE NFPA collaboration, that's how we approached the next edition of IEEE 1584. This project was going to have quite a budget, and the goal was to go on a fundraising mission to raise about $6.5 million. That was the price tag, the estimated price tag for all the new work that was going to be performed. So the fundraising got underway, the collaboration team was put together, the test plan was put together, and things were going really well until the economic meltdown. And the fundraising had taken us up to about $3.5 million, and then, well, we'll say the wheels fell off. So armed with $3.5 million, the next step was, let's get the testing underway. So there was an initial research period, lasted about a year or so. We call it scouting tests, just trying to do some initial testing. So from 2009 to 2012, this thing really kicked into high gear. And there was a lot of testing, and that's what led to the development of the new model. And this ultimately ended up being in a report, the IEEE NFPA collaboration. And then another group was put together. This was handed off to our group, the IEEE 1584 working group. And the working group put together a task team, and they would review the equations and make some refinements, make some adjustments. And ultimately this led to the final report from the task group within IEEE 1584. And this has a lot of their work and tests and so forth. Quite a bit of work went into this. Now what happened next is we took the model, pretty massive amount of equations that I'll talk about here in a little bit. And they put all this together, and we had to put everything into a draft of the next edition of IEEE 1584. Now this took a little bit of doing because we had text from the previous edition from 2002. We were massaging it to fit the new model, and it was quite an undertaking. This whole thing had been quite an undertaking. A lot of people involved along the way. So the draft was created, basically the first draft of the next edition, and we had to achieve what's known as consensus. And all consensus is within the working group, the IEEE 1584 working group. At one time we peaked at about 100 people. It kind of fluctuates up and down. We had to get a consensus from the working group that yes, this draft, this model, everything, we're good with it all before we pass it on for the formal voting. And we finally achieved consensus, and the formal voting is referred to as a sponsor ballot. Now the sponsor ballot, that's kind of the official voting. And what happens here is a separate group of balloters are put together. They sign up. There's a certain process you go through. And we actually had somewhere around 160 balloters that were going to vote on the actual draft. And this is the formal part. Some were working group members. Some are from other areas. We had the first sponsor ballot vote, and it passed. That was really impressive. It passed the first time around. But when you vote, you're also permitted to make comments, and the comments all have to be addressed. So yes, it passed, but we had over 1,000 comments that we had to address. So this was going to be a little bit of a workload ahead of us. So what we did to more efficiently address all the comments is a ballot resolution committee was created. And the ballot resolution committee, it was just a group of 9 of us. And we tried to have it so that it was a whole cross-section of backgrounds that represent basically the backgrounds of the working group. So it was kind of a representative sample. And so the 9 of us, I was one of them. So the 9 of us, we were just in almost an infinite series of phone calls, of web meetings, of face-to-face meetings. We lost a couple of weekends just meeting at different locations, trying to resolve all of this. And it was quite an undertaking. So we got through the first round of comments, a little over 1,000. We developed a new draft addressing many of the comments. And then we went for a second ballot. It's called a recirculation. So voting again. So again, it already passed, but what happened now is we had to change things because of all the comments. So it went around for another pass, came back, and we had a couple hundred more comments. So we had to address those, repeat the process, and this went on for several times, and we are now on draft 6. And draft 6 is right here. So for draft 6, this is the latest and greatest. Draft 6 at this point is the final draft that we have, and that's what this is going to be based on. So draft 6 was sent to the IEEE Standards Association, and the IEEE Standards Association, they have several steps that they have to go through. So it's not over yet. People keep asking, when's it going to be out? When's it going to be out? And honestly, I don't know. There are a few hurdles left. I'm optimistic in saying that it will hopefully be before the end of the year. And I'm hopeful that's the way it works out. But we've had some things happen in the past, and I'm not going to say, yep, it's definitely going to be the end of the year, because I don't know. And I'll talk more about that towards the end of this program. So what's changed? This is the question that I keep getting. Jim, you're so involved in this, and you do a lot of the training for the IEEE 1584 arc flash calculations and arc flash studies. So, what's changed? And I thought about this, and I really need to rephrase the question, because it's not really such a matter of what's changed. I think the better question is, what has not changed? That's an easier one to answer. So I thought about it, and the answer to what has not changed, it still has the same title. That's about it. Pretty much everything has changed. There are a few things that carried over, but the bulk of it is just a complete overhaul. New equations, new methods, new approaches, many different steps, much more robust, a nice way of saying really complex, equations. So what I want to do is walk you through what some of these major changes are all about. The major changes The first one is we have what are called different electrode configurations. I have some diagrams, and I'll explain this a little bit more here in a few moments. The original 2002 tests were based with 3 electrodes in a vertical configuration. Basically, they were oriented down. And so what would happen was the energy would shoot away from the source down to the end of the electrodes, and it'd just come off the ends. That was fine. It was very successful. We got good equations out of it. Again, it was the first of its kind back in the day. But some of the international experts began to question, well, what if the electrodes are in a different configuration? What if they're horizontal? What if they're horizontal in an enclosure versus in air? We already had vertical in an enclosure versus air. And then several years ago, a couple of people found out that, and if you have the vertical electrodes and they terminate in an insulating barrier, and I'll show you some of this in a little bit, it's a whole different animal. So what happened is we ended up with the new model having different electrode configurations. Another thing that happened is the original model from 2002 was based on a little over 300 arc flash tests. The new model, we're up to almost 2,000. It's just under 1,900 tests for the new model, covering a wider range of conditions, different enclosure sizes. We added more enclosure sizes, and I'll talk about all that a little bit later on as well. And also one of the big things is we're trying to cover a continuity over the voltage spectrum. This still goes from 208 volts to 15 kV like the last one. But the 2002 edition, the arcing current was really based on just 2 equations. There was an equation that went from 208 up to 1 kV, just under 1 kV. And then there was an equation from 1 kV up to 15 kV, and that was it. So pick one. And there were no adjustments or fine tuning for actual voltages. That's all we had. So the new one, we widened it out. There are 3 voltage-based equations. There's 600 volts, 2700 volts, and then 14.3. So there are 3, but more than that, you interpolate along the way, because you're thinking, well, 600 volts, my system's at 480. That's still not perfect. Well, once you go through the calculations at 600 or whatever's appropriate for your system, then there's an interpolation that you go through to get this down to your actual voltage. There's also an enclosure size correction factor, because what happens if you have an arc flash and it's in an enclosure, the size of the opening is going to affect the energy. So we have more enclosure sizes or box sizes, but we also have an enclosure size correction factor to adjust if it doesn't happen to fit one of the enclosure sizes that we have. We also have a minimum arcing current adjustment. Now, this kind of parallels what was done in 2002, but it's a little bit different. So you may recall in 2002, it actually came out in 2004, it was an amendment that suggested that for arcing current calculations from 208 up to 1 kV, you multiply the arcing current times 0.85, 85%. Basically, you get a second arcing current point. And use that slightly lower adjusted arcing current and see if there's any change in the clearing time. Basically, did the arcing current fall below some significant point on a time current curve, like fall below the instantaneous or something like that? Well, this was more greatly refined, and there's an equation and a lot of coefficients that you use to develop a more accurate adjustment based on the configurations, based on many other variables. And it applies from 208 all the way up to 15 kV. It's not just limited up to 1 kV as the 85% was. The 125 kVA transformer cutoff. I have had a lot of questions about this one. I'm going to hold off on that one until towards the end, and I'll talk about what happened and why we handled it a certain way. And also the question about the 2-second rule. Actually, the 2-second rule I can answer right now. The 2-second rule, back in the 2002 edition, there's the case, and it still exists, where you may have a situation that you have a lower arcing current, and the protective device acts like it's, or the time current curve of the protective device looks like it's going to have a clearing time that's going to, wait until like next Tuesday or something like that. I mean, kind of an exaggeration, but you get the idea. And so there was some language inserted that said, well, if you have a basically a long clearing time, and if it's reasonable or practical for a person to jump back, because if there's an arc flash, you're reacting. And so if it's reasonable that someone can get out of the way, you could just cut the time off at 2 seconds. People keep asking, you're not going to get rid of that, are you? Is that's still going to be here for the next edition? And the good news is 2 seconds stays. So as of now, as of draft 6, which I'm hoping will be the final draft, the 2 second rule remains. And there was also a question about grounded versus ungrounded. Some of you may recall that there was a configuration that you set up your system as either grounded, like a grounded Y, or ungrounded, like a delta, or even impedance grounded, and you got slight differences in your results. And I'm going to talk about how that was addressed with this latest edition of IEEE 1584 as well. There were some big changes made along those lines. So as far as the configurations, we actually now have 5 different configurations. We have what's called VCB, vertical electrodes in a metal box. That's basically the same configuration that we had in the 2002 model. We have another configuration, it's VCBB, which is vertical electrodes in a metal box, but they terminate into an insulating barrier. And this is something that was, we ran into it several years ago, and it didn't behave like we thought. So we have a new configuration, VCBB. And another configuration, HCB. So those are horizontal electrodes are coming at you in a cubic box. And we have VOA. Actually, VOA was the same thing we had back in 2002, vertical electrodes in open air. And we have a new one, HOA, the horizontal electrodes in open air. And so when you look at all these acronyms, VCB, VCBB, HCB, you understand V is vertical, B is a box, but what's the C all about? Well, this is something that kind of changed along the way. When these terms and these configurations were originally put together, the terminology that we used was VCB, VCBB. And so the question is, kind of a trivia question, what does the C represent? And it simply stands for cubic, like cubic. Yeah, originally the terminology, we called it vertical electrodes in a cubic box, but then we recognized not all the enclosures are cubic. The sizes aren't always going to be the same, and the definition of a cube is all the sizes are the same. So we still have C in there because that's an acronym we've been using. We just got rid of the reference to the word cubic. So if you see VCB and you're thinking, what is that based on? It's kind of a carryover from how this all started when we referred to it as a cubic box. Little piece of trivia there. Now you know. So the VCB, this is a setup that I was part of in the lab several years ago. This isn't a picture of what was done with the next edition. There are photos of the actual test setups for the next edition in the new IEEE 1584 standard. This is very typical of that kind of a setup. So you see the 3 electrodes, and you take it's a fuse wire, I call it a trigger wire, and wrap it around the electrodes, and that basically creates a short circuit. And so then when you close the breaker and you're closing into a short circuit, that wire vaporizes, and then the arc is established, and it runs down, it runs away from the supply, and the energy comes off the tips. And what it'll do is it'll go down and then spill out of the box off of the end of the tips. So my own diagram of this, you have the 3 electrodes in the box, and I put the trigger wire across there. That's not the trigger wire there. That just indicates where the arc is being established. The trigger wire is actually up higher up on the electrodes. And so you get the arc established. This is almost instantaneous. And then the energy, it actually shoots down, but it kind of then works its way out. So it comes down and then out, spills out. And that's the test that we had in 2002, and basically repeated it, refined it, but repeated it. So we still have that configuration for the next edition. And then we have a configuration for the insulating barrier. Now this was a test setup from several years ago. Again, this isn't the exact setup from the new standard. There are pictures for those test setups that you'll be able to see with the new standard. But it's pretty much the same kind of an idea. And so what happened is there was this thought about what if the conductors terminated into an insulating barrier. And this is representative of certain conditions in some types of equipment. And the thought was the arc energy would be running down the bus, and it would hit that barrier, and it would balloon out and basically come out a little more aggressively. And so on the left side, I show the trigger, the fuse wire wrapped around it, and then it's a fiberglass block kind of pushed up with a couple of pieces of wood, 2x4s. And so that's the setup. And my diagram, like this, it just shows, this is actually more what the IEEE 1584 test was based on, what they did. And I say they because it was actually the project team that did this. It wasn't the working group. So what the project team did is they took the 3 metal rods and they put the barrier down at the bottom of the box. And so you got the same kind of a thing. You have the initial arc starting, and then what would happen is the energy would hit the bottom and then kind of be ejected a little bit, come out with a little more authority. That's how we'll refer to it. And so that was the VCBB, as we call it. And then we have the horizontal electrodes. And these are the electrodes pointed at you. And this is the most aggressive of the test, because what's going to happen when you have horizontal electrodes, and this might be like bus stabs or something like that, and I have a few pictures I'll show you, that the energy, it's going to run along the horizontal bus, and it's going to come off the end, basically being directed at the person that, you know, may be in front of it. Hopefully there won't be anybody in front of it. You should be standing off to the side, but it's coming out more aggressively. And so you have the arc, and then you have this, basically the energy that's being directly shot, ejected straight out of the enclosure. And as I said, this is a lot more aggressive of an arc flash setup. And then we had the cases for open air. We have the vertical electrodes in open air. They're just suspended. That's what that little grayish thing is. And you have your trigger wire, and then you have the arc, and then the energy just shoots down, kind of comes down. And this is the same thing that we had, or similar, I guess I should say, to what we had back in 2002. It's been refined a little bit, but it was the same electrode configuration. And then we did add another one for open air. Since we're working with horizontal electrodes, we have the horizontal electrode configuration in open air. And again, this is going to be coming right at you, but not being constrained in a box or in an enclosure. It's still going to be really aggressive, but it's not going to be concentrated as much as if it was coming out of an enclosure or a box. So the idea of having these different configurations is so that you have more flexibility if you want to be more creative in modeling the different types of equipment. For example, the vertical electrodes in air is just, I'll call it a run-of-the-mill arc flash, the way we've been treating it so far, where you have an arc flash, it's in an enclosure, and it just comes out of the enclosure. And that's kind of the way that we've been handling this since 2002, and pretty effectively with good results. Then we have the vertical electrodes in the metal box with an insulating barrier. And it might be something like this. If an arc flash occurs, let's say, up ahead of this breaker, and the energy runs towards the breaker, it hits the insulating properties, and it may behave more like a VCBB type of a configuration. And then we have the HCB, the horizontal. And this might be like where you have stabs or something like that. If an arc flash were to occur, as you see here on these stabs where the fuses go, the fuse mounts, it may tend to behave more like horizontal electrodes coming out at a person. And then we have the vertical electrodes in open air. That's just a basic arc flash in open air, again, similar to what we had in 2002. And then we also have the horizontal electrodes in open air. And this is a little different. This is actually, it's kind of questionable about this one because this is from the secondary of a pad mount transformer. It's a kind of a special design where the side, the top, everything opens up. So it does behave a little more like open air. But, you might argue, can you really sustain an arc flash across that kind of a distance? Don't know. It's the more distance you have, the harder it is to sustain. But there are situations where you may have electrodes that are pointed at you. And in that case, you can use the HOA model. To learn more about IEEE 1584 and also receive updates about when it's finally released, as well as other news, simply sign up for my updates at brainfiller.com/updates. Now, I talked about the voltages, that the 2002 edition really just broke the voltage into two parts. There was an arcing short circuit current equation, and that was from 208 up to 1 kV. And then there was a second equation from 1 kV to 15 kV. And as I said, you pick one, and that was it. And there was no adjustment or fine tuning for whether the 208 to 1 kV, whether you were actually at 208 or 480 or 575 or any other voltage. There was no fine tuning. So what happens with all the testing, we actually have three basic equations now based on 600 volts, and you actually pick a 600 volt model or 600 volt equation, or 2700 volts, kind of a mid-level, or up to 15 kV that was actually tested at 14,300 volts. So there are three equations, and you might think, well, that's not much of an improvement. You had two before. Well, these three equations are for everything. For the arcing current, for the incident energy, and for the arc flash boundary. Plus, this is what's called the intermediate, or I refer to it as the initial calculation. And then what you do is you interpolate. Once you come up with your results, then there's an interpolation procedure that you go through to scale it into your actual voltage. So for example, if you're using 600 volt equations and your system is actually 480, your initial calculations will be based on 600 volts. But then you go back and interpolate and basically change it or adjust it to the 480 volt condition. The calculation steps, there's the intermediate average arcing short circuit current. And that's the initial calculation that I was talking about. Next, you calculate the final arcing short circuit current by interpolating for the actual system voltage. Then after that, there is what's referred to as the minimum arcing short circuit current. So you begin with the intermediate. That's the initial. That's going to be at 600 volts or 2700 or 14.3. And once you go through that, then and you go through all the other calculations for the arc flash boundary, incident energy, then you go back and there's the adjustment factor. Now in the 2002 it was the 85% adjustment factor. Here it's adjusting for the minimum current. As I said, it goes from 208 all the way to 15 kV. So you make your adjustments for the minimum current, and then what you do is you take this minimum current, kind of like the 85% that we had. You look at this minimum arcing current and you evaluate the time current characteristic and determine, well, did the clearing time change? By using the minimum current, did that maybe drop below an instantaneous setting? And now we have a time delay. So it's similar to what we had with the 85% multiplier back in 2002. Well, it came out in 2004 with the amendment. But it's a little more robust, and it covers the entire spectrum. And then we also have an adjustment for the enclosure sizes. I'm going to show you there are many more enclosure sizes this time around. But if you want to fine tune it even further, there are factors that you can develop, that you can calculate, where you can further make adjustments for the size of the enclosure based on specific conditions. And then we also have the calculations for the incident energy, the intermediate, or we'll say the first pass, and then you go back and fine tune that, interpolate for your specific voltage and the arc flash boundaries. So it's a much more robust process that we have this time around. From the 2002 edition of IEEE 1584, we just had a handful of what we called classes of equipment. And those of you that use software, this is one of the functions that you set up on the software. It asks you, it usually says like equipment type. It's really class, but it'll say equipment type, maybe it says class. And you select, is it medium voltage? Is it low voltage? Usually like distribution equipment, panels and switchboards. Or is it low voltage power equipment, like low voltage switchgear? And so these were the basically the categories that you had, the equipment class. And the bus gaps, the gap between the bus bars, they're just kind of typical. Most people leave these because you don't know what else to use. And within any piece of equipment, you can have different spacings at different locations in the equipment. And then these are the enclosures that were used for the original 2002 standard. Well, with, as I said, almost 1,900, approaching 2,000 new tests, this was greatly expanded. And so starting at the top, we have 15 kV switchgear. We're still using the 152 millimeter gap, same thing that we had before. And we have an enclosure of 45 by 30 by 30. And then we had 15 kV motor control center, 152 millimeter gap, but the size is smaller for motor control center. And then we have 5 kV switchgear of a larger enclosure size, and then 5 kV with a smaller enclosure size. 5 kV motor control center, low voltage switchgear. And then a new thing that we have is for low voltage equipment, and I'll talk about this more, we make a distinction between whether it's shallow equipment or whether it's standard or typical equipment. And the distinction is it's below 600 volts, and there are certain size parameters, but it's really with depth. That up through 8 inches, that's going to be considered shallow, and then over 8 inches in depth, that'll be considered a typical size piece of equipment. So there's a distinction, and I'll talk more about that a little bit later on. And then cable and junction boxes at the very bottom of the table. The enclosure size correction factor. So when you're going to perform your calculations, you have to select the proper equipment class, the voltage, the type of equipment, as close to whatever enclosure size you have, what you might consider to be representative. But if you want to fine tune it, there are calculation methods where you can take the equipment class and whatever size was given for that class, and you can adjust it for more exact parameters that you may actually have. And so to begin with, you have to determine, okay, is this going to be, it's an enclosure, so it's VCB, VCBB, or HCB. Those are the only 3 for enclosures. So you have to select, which one of these you have. And up through 600 volts, you have the distinction between typical and shallow. And as I said, up through 600 volts, the height and the width can't exceed 20 inches. And then the depth, up through 8 inches, that's shallow, and then greater than 8 inches, that's going to be considered typical or normal. So as far as the correction factors, and there's a whole calculation process you go through for this. We have what's typical and what's considered shallow. Typical is most commonly what you're going to be using for low voltage, for medium voltage up through 15 kV. But again, for low voltage, less than 600 volts, if it's classified as shallow, there's a different adjustment that you can make. The arcing current variation, I want to talk a little bit more about this. I mentioned it earlier. So in the 2002 edition, we had this 85% multiplier that was, as I said, brought out in the 2004 Amendment A, where you take the arcing current, multiply times 85%, because there are a lot of unknowns. And the real concern was, well, what if we calculate this arcing current? We have what seems like an exact number, lots of decimal places. That's a little misleading. And what if the actual arcing current for a real event maybe is less than that? What happens? And so that's why the 85% was introduced. And it was only up through 1 kV. So this time around, it's a more robust set of calculations, and it applies all the way up through 15 kV. So this adjustment, it's really to determine basically a minimum of what the arcing current may be. And then you look at this minimum arcing current, look at your time current curve to try to determine, okay, so with maybe the minimum, the low end, would that affect the clearing time? Because as many of you know, the clearing time is going to be a function of the current. And if it's all up in the instantaneous and the average and the minimum are still in the instantaneous, well, then it's not a big deal. But if the minimum drops you below the instantaneous, or maybe drops you into a short time delay or something like that for some of the electronic trip breakers, you're going to want to do a little more work on this. So the arcing current variation factor, as I was talking about, the 2002 edition of IEEE 1584 used 85%. It was in the 2004 Amendment A, as I mentioned. And the thought was, if you calculate this arcing current, and there could be all kinds of decimal places, which is misleading. It's like, oh, this is really exact. It's an estimate at best, and that's actually how we used to reference it, kind of an estimated arcing current. What if the actual arcing current was lower? You might think, well, if it's lower, then it won't be as much energy, will it? Well, it won't be as intense, but what could happen is the lower current could end up maybe resulting in an upstream protective device that's going to maybe define the arc duration. Maybe that device will take longer to operate. So it's not as intense, but you have more duration, which could actually be the worst case. So that's what that 85% was all about. And so what we've done now is we have a more robust calculation process that spans over the entire range from 208 to 15 kV. Okay, the question that everybody keeps asking. there was language in the 2002 edition of IEEE 1584. It actually appeared in two different locations that stated that equipment below 240 volts, which kind of implied 208, doesn't need to be considered unless it involves at least one 125 kVA or larger low impedance transformer in its immediate power supply. So the size of the transformer, what that had to do with it, is the thought was smaller transformers are going to reduce the short circuit current. And if this is down at 208, there were just a couple of tests that were performed that indicated that it's really going to be difficult to sustain. So can you have an arc flash? Yeah, but is it going to sustain and be what at the time was considered, to be a significant hazard? No, not really. And so that's why this language was included. Now, some people are thinking, well, that was deleted. No, not really, not from the original source. What happened, if you're thinking, it was deleted, that the 2009 edition of a different standard, NFPA 70E, will say borrowed this language. They didn't quite get it the exact way that we had it. They said equipment 240 volts or less, and here it's actually below 240. But anyway, so they borrowed it. It was introduced into the 2009 edition of NFPA 70E. This is the origin. It came from IEEE 1584. And then in 2012, they deleted it. So, if you're thinking, oh, it doesn't exist anymore. Well, it doesn't exist in NFPA 70E. It really didn't belong there anyway. The origin is IEEE 1584. So what this was all about is if you're performing arc flash calculations on the secondary side of a small transformer at 208, and let's say the arc flash occurs somewhere between the main and the transformer, or the main piece of equipment. Normally what you're going to do is you're going to look at the duration of the arc flash being defined by a device upstream, which would be a primary. And you start looking at how long it takes a primary device to operate. It could be a while. And so you end up with some pretty extreme, you could end up with some pretty extreme numbers for your incident energy calculations that may not be realistic. And that's why this was placed in here. So the question everybody's asking, is the 125 kVA transformer going to stick around? Let me explain. So I have a couple of tests here. And this first one is just a small panel. And it's downstream from a branch breaker. And this is, kind of a typical, we'll call it a really low level, almost an amusing arc flash. I'm guilty. I've done this more than once. So let's take a look. You really had to be looking for it. Just a little pop on the side. And that was kind of along the lines, was there an arc flash? Yeah. Was it a hazard? Well, I guess it could, eject a little bit of metal and maybe cause a problem with your face or your eyes. But it wasn't anything really earth-shattering. And so we'll take a look at maybe kicking it up a little bit. In this next case, this was a bus plug. And with the bus plug, you can see the shorting wire up on the line side. And it was a little more dramatic arc flash. This was a lower current. This was, I believe it was 208. And let's take a look at what happens. 400 amp bus plug, 400 amp fuses. I ran some numbers based on the 2002 edition of IEEE 1584, just looking at typical transformer sizes and a pretty typical impedance, and looking at the incident energy based on 1 cycle, 6 cycles, 10 cycles, 20, and 30 cycles. And with a 112.5 kVA transformer, you cross over that magical 1.2 calorie per square centimeter threshold where protection is going to be required. It's often referred to as the onset of a second-degree burn, where that could occur. And you cross over that at 6 cycles, so you'd have to have a pretty fast extinction. For a 75 kVA, it's going to take a little more duration, and you can see the trend, 45 kVA, 30 kVA. So that's a little bit of what drove the language from the 2002 edition of the standard. And then, quite a few years ago, there was a question about what if the electrodes terminate into an insulating barrier? And this is a setup of some of the original work with the insulating barrier. Now, I was in the lab when this was being done, and then 2 colleagues of mine wrote a really good paper about this type of a setup. And so what happens is the arc flash initiates where the trigger, the fuse wire is, and the arc and the energy runs down and it hits the barrier, as you can see, and then it kind of balloons up. Now what the big thing was here is if you use an insulated barrier for low current and low voltages, the original test, the original thought, if you didn't have the barrier, that the energy would just come off the tips of the electrode, boom, blow itself out, and that was it. But with a barrier, what happens is it kind of captures it a little bit, the plasma. And it's sort of, think of it as like puddling up, and it sustains, and it actually can flare out. So this next test, I was in the lab. This is one of the earlier tests coming up, and I'll just say I was surprised. This did not go like I thought it was going to. I thought it was going to be just another pop, and no, that's not what it was. So, as I said, I was kind of surprised. So, where's this taking us? There was a lot more research with the barrier tests and with lower currents and lower voltages. And what we found was the 125 kVA exception. It's not really an exception, but that's how people refer to it. The 125 kVA exception is a little bit optimistic. And so, after extensive testing for the next edition of IEEE 1584, the new language just simply states that sustainable arcs are possible, but are less likely in three-phase systems operating at 240 volts nominal or less with an available short circuit current below 2,000 amps. And so the way it stands right now, with the next edition of IEEE 1584, the 125 kVA exception is gone. And in its place is a reference to 2,000 amps. And still a possibility of sustaining, but not as likely. Grounded versus ungrounded. In the 2002 edition of IEEE 1584, when the arc flash tests were established, the first fraction of a cycle or so, it was really erratic. Then we'd hit more the stable part of the arc. And so what was happening, the equations reflected a difference in incident energy between whether the system was grounded or ungrounded. Let me explain why that was, and then what was done to address it in the next edition. So first off, when you perform power system analysis, power system calculations, what we typically do is you take a three-phase power system, and if it's balanced, we perform what's known as a per-phase analysis. You just analyze one phase, because if it's balanced, you're going to have the same result for phase A, B, and C, so I'm not going to calculate it 3 different times. So you calculate it once, a per-phase representation. And this is an example of a per-phase representation for a three-phase short circuit calculation. You look at one phase, you have the short across there, you look at the values, and you come up with your answer for the one phase. And that's a per-phase analysis. Well, an arc flash study, the arc flash calculations, they're based on three-phase systems. And we were assuming that it was all balanced. When you get a stable arc, it's fairly balanced. But that initiation period, we captured that with the 2002 edition, and it affected the way the equations were developed. And so you get 2 different results. So to give you an example, this is from 2002, of the difference that you can have between a grounded or an ungrounded system, both with a box, an enclosure, and an open air. I ran a few numbers. This is from the 2002 standard. And for example, a grounded system, you have a coefficient, it's called K2, and that varies depending on whether it's grounded or not. So for the grounded case, for an enclosure, there's 4.6 calories per square centimeter. Whereas if you select ungrounded, there's a different coefficient, K2, it's actually 0. For ungrounded, that number goes up to 6 calories a square centimeter. So there was a difference in the way you handle this. And then for air, there was also a bit of a difference, grounded versus ungrounded. For the next edition of IEEE 1584, all of the data was analyzed, and it was placed sequentially from maximum to minimum, and the 2 lowest cycles were kicked out. And that's when you get into this basically mix, where it's partly a bolted short circuit, the wire is melting, the fuse wire, it's transitioning to arcing, it's really erratic, and it actually behaves a bit unbalanced which is why grounding factored into this, because you had a bit of an unbalanced current there in the beginning. So the new equations are based more on the stable arc, and because of that, there's no difference between whether your system is grounded or ungrounded. It's, we'll call it one size fits all when it comes to grounding for the next edition of IEEE 1584. Now the calculation process, it's going to be a little more complex. This is a flowchart from the book that I wrote years ago about how to perform arc flash studies. And in that process, I have a lot of the details grayed out, but the arc fault calculation, the arcing short circuit calculation, and the incident energy and the arc flash boundary, those are the three key numbers that you were calculating with the 2002 edition of IEEE 1584. Well, we still need these values, but how we go about this is completely different. As I mentioned, there's a calculation of the intermediate values, and then you fine-tune it based on your specific voltage. So what happens, this is just kind of a simplistic view of how this plays out. You select the appropriate equation based on the voltages, 600, 2700, or 14,300 volts. And so there's three different equations. There's all kinds of coefficients that are going to be dependent on the voltage that you select. And you calculate the intermediate value, I call it the initial value, of the arcing current, the incident energy, and the arc flash boundary. And then for each one of these, you interpolate for your actual voltage. So as I mentioned earlier, let's say you use a 600 volt equation and you're calculating for a 480 volt system. Well, your initial calculations will be based on the 600 volt model, but then you interpolate and adjust this to the actual 480 volts. And then you go back and you readjust the arcing short circuit current to find the minimum arcing short circuit current. And as I mentioned, if that happens to change the clearing time, then you're going to want to go back and repeat the calculations for the longer clearing time. And whichever case is going to be the worst case, and if you have a longer clearing time, that'll probably be it. That's what you're going to use for your result. The calculation steps. All I can say is strap in and hang on. Here we go. This is the process that we're going to be going through with the next edition of IEEE 1584. The first step is you calculate the intermediate average arcing current, as I mentioned earlier. And then you calculate the final arcing current. That's the interpolation. So you pick either 600 volts or 2700 or 14.3, and then you interpolate for your specific voltage. And then you're going to calculate the incident energy. Well, before you do that, you select your enclosure type, basically your class of equipment, and that'll default to a certain enclosure type. And then if you want, you can adjust that for the size correction factor to be even more accurate. So with the size correction factor and the arcing current, you calculate the intermediate incident energy. And again, intermediate just means it's going to be either 600 volts or 2700 or 14.3. And then you calculate the final incident energy by interpolating for the voltage. And then you calculate the intermediate arc flash boundary. Again, it's basically just saying the 600, 2700, or 14.3 kV version of the arc flash boundary. And of course, then you go back and you interpolate for the actual voltage. So it's much more precise to be able to handle it this way. And then you go back and you calculate the adjustment factor, the variation factor, to determine the minimum arcing current. So then you adjust the intermediate, not the final, you adjust the intermediate arcing current using the correction factor, and then go back and redetermine the final arcing current with the interpolation. And then you go back and recalculate the intermediate incident energy and the final incident energy and the intermediate arc flash boundary and the final arc flash boundary. And all I can say, got to throw a big warning out here. Your brain may explode on this one. This is much more robust. It's a much more elaborate process, many more steps. One set of the calculations actually has 13 separate coefficients that are used and the interpolation. So there's a lot that goes in with this. So people are really going to be looking to software to solve this. And actually, as far as the software, I should go ahead and bring that up right now. I also get the question about, are the software companies, and you know who they are, there's a lot of majors out there. Are the software companies up to speed on this? Are they going to be ready to roll this out? And actually, representation from all the major software companies are on the IEEE 1584 committee. In fact, they all had a hand in reviewing and evaluating and fine-tuning the model from the project team. So yes, the software companies, they've all had representation. They've all been really integral into the development of all this. And they all have, to my knowledge, I've talked with quite a few of them, they all have basically their software ready to go, just waiting for the approval that the next edition is ready, and they'll be out there. So they've been a very integral part of the working group in the development of all this. A couple other things that came up from the test. Light is considered to be an issue, of course. The ultraviolet light can cause blindness, temporary, permanent. So there were some tests performed for light. Now, just as a benchmark, a frame of reference, we use the term lux for the unit of measure, and lux is just 1 lumen per square meter. It's just the definition of the illuminance level. And so give you some idea, some basically frame of references for what we're talking about. Around 1,000 lux is just a kind of a typical overcast day. You go up to 100,000 lux, and that's a really bright, direct sunlit day. So that's kind of give you a frame of reference. Now, from some of the arc flash tests, 3 meters away, there have been recordings of over 1 million lux. And there was one that actually went up to a little over 13 million lux, over 130 times brighter than the sun. That's going to be a tough one. And yes, light is one of the hazards. I've told the story in my training classes over the years that several years ago when I was performing arc flash tests in the lab, I have a camera that I set up, and I have the lab tech who actually hits the button to close the breaker and launch the arc flash. I always have him count backwards. He goes 3, 2, 1, and then boom. And so on this one occasion, I had my camera and I was adjusting, and I was kind of looking out there, getting it all focused, and it's it's probably about 20 feet in front of me. I wasn't right in front of it, and I'm behind the glass. I think it was bulletproof glass. But it was just like I was stunned, and I kind of shook it off and looked up. I couldn't see right in here, my field of view. It was like a real bright purple, really weird. But I had to try to shake it off. There were a couple other people in the test booth, and I'm thinking they're going to think I'm an idiot doing this, because I thought I messed something up. And then I went back and watched the video later. My sight came back over about 15, 20 minutes. And so then I went back and looked at the video, and it just turns out there was no countdown, no 3, 2, 1, just boom. And I was still focusing the camera. So that's some new information that we have regarding light. This really won't be rolled into the 1584 standard, but it was some really good test data that we ended up with. And then also blast pressure. Blast pressure is still something that we're scratching our heads. The thought is, yes, if there's a really significant arc flash, and it's really more short circuit dependent, that you can have a pretty significant blast pressure. But the measurements are showing that the pressure is somewhere between 100 and 250 pounds a square foot. I mean, it's significant, absolutely. It can knock you off a ladder, off a scaffold, do all kinds of things like that. But there was sort of what I called the urban legend years ago, where people would say, oh, it would just blast you right into the wall, and basically it'd be a bug splat, that kind of thing. And there are all kinds of sensationalized, stories along with that. It could be significant, but, knock you back and rough you up and knock you over, hurt your head, something like that. But I've never heard of a case where it's actually slammed somebody, basically turned them into well, anyway, use your imagination. So upwards of 100 to 250 pounds a square foot. So we'll be looking at this probably in the future, some type of new modeling for the blast pressure. There were some older kind of theoretical models and some other models that are out there, but we'll be working on this perhaps in the future sometime. By the way, with this blast pressure thing and, about it blasting you into the wall and the bug splat comment that I made, the 40 calorie per square centimeter note that was in NFPA 70E, that's what set off a lot of that. It was something that was brought in the 2000 edition. And over the years, people began to recognize, well, it's not so much a function of calories per square centimeter incident energy. as it is about short circuit current. So the latest edition of NFPA 70E just simply removed it, and with really good reason. What they did is they stated that, what's 40 calories have to do with de-energizing? That's what this was about. Above 40 calories, should be a big emphasis on de-energizing. And the rationale was, what's 40 calories have to do with this? You should always de-energize. So that was a genius move to handle it that way. The sound pressure. So hearing protection, I think, as most people know, is required, at least according to NFPA 70E. And the sound pressure could be absolutely staggering. As a frame of reference, conversational speech is approximately 60 dB. dB, decibels, that's the measurement that we use for sound pressure. This is actually sound pressure. And you take this up to 120 dB, and that's like a very loud rock band. And actually, I had to dig through all my photos. That's one I took a long time ago, back in my rock concert days. I think my ears are still ringing to this day from those guys. But you get the idea. Sound pressure goes up. And with an arc flash, we've had some measurements with an arc flash. And a typical arc flash, the sound level is about 140 dB. I mean, it's an impact. It's not sustained. But 140 dB, I mean, that could cause some hearing damage. And some tests have actually recorded the sound pressure upwards of about 170 dB. I mean, that could just destroy your ears. So sound pressure, I mean, it's very significant. And wearing hearing protection, this is why. And so we have some more data, some more tests to support what can actually happen during an arc flash. So what's next? We're not done. There's going to be more work. Just because the latest edition of 1584 is about finished, and I said there's a few other hurdles that we have to clear yet, but it's almost finished, doesn't mean we're done. There's a lot more that we want to look at. And this is in no particular order, and there's no guarantees that this is exactly how we're going to handle this. But some things that we're kicking around, this first one actually is a guarantee. That's what we're going to take up at the next meeting. It's a revision of what's called IEEE 1584.1. And IEEE 1584.1 is basically what goes into an arc flash study, the scope and deliverables of an arc flash study. So since 1584 has been completely overhauled, we have to bring 1584.1 in sync with 1584. So this will be one of the first things that we begin to undertake. DC arc flash, that's still kind of up in the air. The book that I wrote years ago, I have a chapter in there about DC arc flash. I didn't come up with a method, but I'm the one that kind of went public with it. It was based on some really good technical papers by some really well-regarded and well-respected people in the industry. So there's a method out there. It's just not based on any kind of a standard, but the industry's kind of embraced it so far in the absence of anything else. But hopefully in the future, we'll be able to start moving forward and do a little bit of work on DC arc flash. The lower current cutoff, well, right now it's 2,000 amps. Are we going to be able to work with that anymore? I'm not sure. Because the problem with trying to come up with a low current cutoff, as I said, it's not a hard, fast number. There's the possibility under certain enclosure sizes, certain configurations, and smaller gap distances, you could sustain to some really low values. So that one's kind of up in the air at this point. Higher voltages, that's something that we've talked about. The standard goes up to 15 kV. Maybe someday we'll be able to take it above 15 kV. Who knows? Stay tuned. And then many other areas. There's just so many other areas. And if you put this into perspective, we're only on the second revision, the second round of research for a standard. The 2002 edition, way back then, as I said, was one of the greatest things when it came to arc flash that the industry's seen. And now, 16 years later, we've added so much more to it. So there's so much more that we've covered that we never even thought about, or well, I shouldn't say we didn't think about it, but that we didn't address back in 2002. And so now what we'll do is we'll start looking at what if, where are we going to take this thing next? And who knows? Many of you know my website, brainfiller.com, kind of an odd name, but everybody remembers it. And periodically, I'll write updates out there based on direction, things that we're looking at. Some of you've probably seen some of these updates. And I also have the website is called arcflashforum.com, and I do similar things there. So, if you have ideas or questions or, hey, what's going on, put it out there on the ArcFlash forum or send me an email, and I'll give you my email address here at the end. So, still getting the questions. Are we there yet? And actually, back in 2012, some people were saying, oh, it's done. It's going to be out within the year. It's like, no, it's not. So the Are We There Yet's been going on for quite a while, and more Are We There Yets and more Are We There Yets. So, are we there yet? We're really close. The draft right now, draft 6, as I said, it's with the IEEE Standards Association. There are certain hurdles that have to be cleared on that part yet. But as far as I know, draft 6 is going to be it. Now, I mean, something could happen, but I'm pretty sure the model, the draft and everything, it's going to be as it stands. If not, well, you'll be getting an update, but it should hopefully be going through. But as I said, it's probably not going to be until towards the end of the year by the time we clear all the rest of these hurdles. So we're really close. And after 16 long years and lots of people, I mean, the working group peaked at around 100, and there have been a lot of people coming and going over the years. It's been a massive undertaking by a lot of people. If you want to be one of the first to know when the next edition of IEEE 1584 comes out, when we actually get the green light, one of the best ways to do this is subscribe to my newsletter. Yeah, it's kind of a cheesy plug. But what this is all about is when we get the notice that 1584 has actually been approved, the chairman, myself as vice chairman, the secretary, we're going to be the first to know. We'll get contacted like the moment it happens. And what I do is I already have it in the queue, basically the release that, hey, it's out. So if you're on the list, you'll be one of the first to know about this. And I'll launch it like, hey, it's done, here we go, and start following it up with a lot of follow-up articles, including follow-up training. I have my new schedule already put together for when this comes out, and it's a pretty aggressive schedule. I haven't had we'll call it a tour schedule like this in a long time. I train nonstop all over the country, actually all over the world, but it's usually for individual companies. And a public schedule like this, I haven't done this in a while. It's a pretty ambitious, aggressive schedule. And planning on the first class for the new 1584 and arc flash studies to just be right here where I'm located, Scottsdale, Arizona. And then from there, I roll on to San Francisco, Houston, Anchorage. Like Anchorage in February? Are you serious? This is actually sponsored by another group that wanted to do this class up in Anchorage. So, okay. New York City, Portland, Oregon, Philadelphia, San Diego, Denver, Colorado, Spokane, Washington, Chicago, Orlando, Boston, Raleigh, Washington, D.C., and then the end of the year, back home again. So if you're interested in more details of this, take a look at the website. Give us a call. Our program director's email and phone number are there. And set yourself up for one of the classes next year, because I'm going to go into a lot more detail than I did here. So for the class, I'm going to be going through the derivation, a lot more behind the scenes, how everything works. We'll be going through some actual manual calculations. You'll get a really good feel for how all this comes together. Some modeling ideas, because, having so many electrode configurations, that's got a few people scratching their head, So that'll be coming around beginning at the end of the year, assuming that everything goes through with the standard being approved. If you want to stay in touch, if you have questions, the best way to get a hold of me is email. I'd say give me a call, but I'm never at the office. This is pretty rare that I'm in the studio today doing this. I'm usually traveling or on the road somewhere, but shoot me an email. You could post questions out at the ArcFlash forum. Twitter, not on there as much, but yeah, there's Twitter. LinkedIn is a pretty good way. And a lot of the videos, including this one, will find its way out on YouTube. So a lot of ways to stay in touch. So I hope this overview gave you a much better understanding of why it took 16 years to get to this point for the next edition of the standard, and kind of everything that happened along the way. And more importantly, I hope this gives you a little better understanding of some of the changes that are going to be coming down the road, and why some of the changes were made, and how they're going to affect your calculations and the whole process. It's a much more robust method, more detail, and much more accuracy. So I appreciate you watching, and have a great day.